Hey guys, welcome to Easy Academy. Today we're going to be learning about sampling distributions and some rules that come with them. So what exactly is a sampling distribution in the first place? So let's take this population of fish over here. Each of them have their own length. This one's 5 inches, this one's 6 inches, and the average length of all these fishes of this population is 5.5 inches with a standard deviation of 1.8028 inches. So let's say I want to find a sample statistic. So I chose to sample 2 fish from this pond and find their average length. So let's say I randomly choose this fish and this fish. The average length of these fishes would be 4 inches because 5 plus 3 divided by 2 is 4 inches. So this process can obviously be repeated. So I could do another random sample and get this fish and this fish over here, and that average would be 3 plus 6 divided by 2, which is 4.5 inches. So the sampling distribution of the statistic is a distribution of values if I were to take every single possible sample of 2 fishes from this population until I get no new combinations. Then I get all the values, the 4 inches, 4.5 inches, and all the other combinations I had, and then I create a distribution of that. That's what a sampling distribution is. Alright, so I finished finding all the values for the sampling distribution right here. As we can see, 5 inches, 3 inches, the average is 4, and so on. I completed every single combination, and these are the values that I got. So now let's go over some general rules of the sampling distribution. So the first rule is that the mean of the sampling distribution is equal to the mean of the population. So if we were to add up all these values of the sampling distribution and find the average should be the same as the population mean, to be 5.5 inches. And if you add up all these values, you should see that that is true. So that's the first rule of sampling distributions. The second rule is that the standard deviation of the sampling distribution can be denoted by the standard deviation of the population over the square root of the sample size. So in essence, the standard deviation of this distribution right here should be the standard deviation of that distribution is equal to the standard deviation of the population over the square root of the sample size. So if we were to find the standard deviation of this distribution right here, we would plug in the standard deviation of 1.8028 inches over the square root of 2. And if we simplify this number down, the number should come down to be about 1.2748. However, there's one more thing we need to check before we know for sure this is the standard deviation of our sampling distribution. We need to check if our sample size is too big. So what is too big specifically? Well, it is too big. A sample size is too big if it's more than 5% of the population. So let's check if our sample of 2 is more than 5% of the population. Well, as you can see, our population is equal to 4 fishes, while the sample size was 2. So, of course, our sample size is way more than 5% of the population. So what do we do now? We multiply our standard deviation by something called a correction factor. Now, the correction factor is denoted by this. The correction factor is equal to the square root of the population size subtracted by the sample size over the population size subtracted by 1, and everything is square rooted. So now we can multiply our standard deviation here by the correction factor. And for that, we know that our population is 4 subtracted by the sample size of 2 over 4 subtracted by 1. And if we put this into our calculator, we can see that our standard deviation for the sampling distribution right here should be 1.0409. So the third rule of sampling distributions is that if the population distribution is normal, the sampling distribution of any sample size of n is also normal for the sample statistic. So for example, if your population distribution looked perfectly normal like this, then the sampling distribution, no matter how many whatever sample size you want to choose, 2, 3, 4, or 100, the sample distribution should also look normal. Now, the fourth rule for sampling distributions is the central limit theorem, which essentially states that if the n, or sample size, is sufficiently large, or by sufficiently large it means that n is greater than or equal to 30, the sampling distribution is approximately normal, even if the population distribution itself is not normal. So if the population distribution does not look like it's normal, the sampling distribution can also still be normal as long as n is greater than or equal to 30. So why exactly are these 4 different rules super important? Well, the importance of these rules is that we can find probabilities using these normal curves, standard deviations, and the means. So we can use this by using a function called normal CDF on your graphing calculator. So first you want to click second and the vars button, and then you go to the normal CDF function, and then you can input lower bounds, upper bounds, the mean, and the standard deviation to find the probability of certain statements. Alright, so now let's do a practice problem incorporating everything we just learned. So here it says the length of fish in a pond has a normal distribution with a mean of 10 inches and a standard deviation of 3 inches. What is the probability that you randomly select one fish from the pond that is between 7.5 inches and 12.5 inches? And what is the probability that you randomly select 3 fish with a mean length between 7.5 and 12.5 inches? So for the first question, it's asking us to only select one fish from the pond. So we can use our population parameter because it's only one fish. And because we know that the pond has a normal distribution, we can use normal CDF. So as we know, normal CDF has the parameters of a lower bound, upper bound, mean, and standard deviation. So we can use the population parameters of 10 inches and standard deviation of 3 inches. So let's input those parameters into our normal CDF function. And we get the lower bound, which is 7.5 inches, the upper bound of 12.5 inches, the mean of 10 inches, and the standard deviation of 3 inches. If you insert this into your calculator, you should get that this is equal to 0.5953. So the probability that I randomly select one fish from the pond between 7.5 and 12.5 inches would be 59.53%. Now for the second question, it's asking us if we randomly select a sample of 3 fish. So now we have to use the sampling distribution. Can we use normal CDF? Well, remember the third rule of sampling distribution says that if the population has a normal distribution, then your sampling distribution should also be normal. So yes, we can use normal CDF. So for normal CDF, we have to implement the same parameters of lower bound, upper bound, mean, and standard deviation. However, the sampling distribution has different parameters from the population distribution. Although the mean stays the same, because if you remember, the first rule of sampling distributions is that the mean of the sampling distribution is equal to the mean of the population distribution, so 10 stays the same. And for the lower bound and upper bound, both are still 7.5 inches and 12.5 inches, so we can fill those in right now, 7.5 and 12.5, and the mean of 10 inches. However, if you remember, the standard deviation changes because the standard deviation of the sampling distribution is equal to the standard deviation of the population over the square root of the sample size. And if you plug in these numbers, it would be the standard deviation of 3 over the square root of the sample size of 3 fish. And this would be equal to 1.7321. So the standard deviation changes for what we have to put in for the parameter of the sampling distribution. So we can implement 1.7321 here. And now we can find out what this is equal to. This is equal to 0.85109. So the probability that I randomly select 3 fish with a mean length between 7.5 and 12.5 inches would be 85.109%. Now we're just going to assume for the standard deviation that 3 fish is less than 5% of the population of all the fish in the pond. So if it wasn't, we would have to implement a correction factor. But because we don't know the population size, we're going to just assume that 3 fish is less than 5% of the population. So we don't use a correction factor.
I tried so hard.